entire purpose of modeling in machine learning is to find a model which tells you which variables are important and how do they interact together to drive your dependent variable. And so you'll find in practice the difference between using like tree space or random forest space to find your nearest neighbors versus like Euclidean space is the difference between a model that makes good predictions and a model that makes meaningless predictions.
Shoot. So, you can hear me now. I've been talking for exactly 10 minutes and you couldn't hear me. I apologize for that. Sorry. So I'm actually going to repeat what I just said. All over. I don't mind. Let's start off with a good morning, good evening, good time of day, good afternoon, all of the goods. Yes, so let's do a recap of where we have been. Since the past few days, as you can see by the title, we are in the 6th live of this introduction to machine learning for coders, which you can see right behind me. We are taking the fast.ai's introduction to machine learning for coders, and I went over the lesson 1, which is introduction to random forests, and then we dived into random forest with the random forest deep dive in lesson 2, and technically I started lesson 2 2 lives ago, but I didn't finish. It was just the first 10 minutes in the first one, and then yesterday we did like 50 minutes, and today I think I will be able to finish lesson 2. And if you go to the notebook, which is on GitHub, you can access it through Jupyter Notebook, but I'm using it on Kaggle. Both of those lessons are still using lesson 1, which is was a bit confusing for me at first, but yes. So yeah, we will continue in lesson 2 right now. I wanted to have a recap / I don't know, maybe a wrap up, so that if anyone joins the live when it's not live, to watches it later, they can see where we are, even though I tried to put that in the title as well. Okay, so yes, now I'm not talking to myself. Okay. So yeah, I will continue with lesson 2, where Jeremy Howard is explaining more about random forests, forest ensembles, and all of that. I think, yes, he said
interact together to drive your dependent variable. And so you'll find in practice the difference between using like tree space or random forest space to find your nearest neighbors versus like Euclidean space is the difference between a model that makes good predictions and a model that makes meaningless predictions. Melissa, do you have?
We queued for a break.
I did, but I feel like we've got only 35 minutes, so yeah.
this is exactly where I stopped yesterday, so now I continue.
Great. So in general, a machine learning model which is effective is one which is accurate. When you look at the training data, it's accurate at predicting, at actually finding the relationships in that training data, and then it generalizes well to new data. And so in bagging, that means that each of your individual estimators, each of your individual trees, you want to be as predictive as possible, but for the predictions of your individual trees to be as uncorrelated as possible. And so the inventor of random forests talks about this at length in his original paper that introduced this in the late 90s, this idea of trying to come up with predictive but poorly correlated trees. The research community in recent years has generally found that the more important thing seems to be creating uncorrelated trees rather than more accurate trees. So more recent advances tend to create trees which are less predictive on their own, but also less correlated with each other. So for example, in scikit-learn, there's another class you can use called extra trees regressor or extra trees classifier with exactly the same API. You can try it tonight. Just replace my random forest regressor with that. That's called an extremely randomized trees model. And what that does is exactly the same as what we just discussed, but rather than trying every split of every variable, it randomly tries a few splits of a few variables, right? So it's much faster to train. It has more randomness, okay? But then with that time, you can build more trees and therefore get better generalization. So in practice, if you've got crappy individual models, you just need more trees to get a good end-up model. Melissa, could you pass that over to Devin?
Could you talk a little bit more about what you mean by like uncorrelated trees?
Yeah.
So here's my theory. When you want to get expert opinion on something, you first check with people who know different parts of the information, right? You don't go to people who give you the same answer, I think, like logically speaking. Just overall, if you want life advice, you go to people who give you different life advice instead of everybody pointing you to the same thing. So I feel like this random forest idea is the same. I mean, not the random forest, the different one, where you want it to give you different features and then average that out. I think that's how they're doing it.
If I build 1,000 trees, each one on just 10 data points, then it's quite likely that the 10 data points for every tree are going to be totally different. And so it's quite likely that those 1,000 trees are going to give totally different answers to each other. So the correlation between the predictions of tree 1 and tree 2 is going to be very small, between tree 1 and tree 3 very small, and so forth. On the other hand, if I create 1,000 trees where each time I use the entire data set with just one element removed, all those trees are going to be nearly identical, i.e. their predictions will be highly correlated. And so in the latter case, it's probably not going to generalize very well. Whereas in the former case, the individual trees are not going to be very predictive. So I need to find some nice in between.
Some nice in between, not all the same,
yes,
but also not so different that you can't have them give you an answer together.
And is there a case where you want to use one over the other, like any particular times?
Yeah, so again, hyperparameter tuning. So okay. Do you mean in terms of like random forests versus extremely randomized trees? Yeah, so again, a hyperparameter, what tree architecture do we use? So we're going to talk about that now. Can you pass that to Dina?
Yeah, I was just trying to understand how this random forest actually makes sense for continuous variables. I mean, I'm assuming that you build a tree structure and the last final nodes you'd be saying like maybe this small node represents maybe a category A or a category B, but how does it make sense for a continuous target?
So this is actually what we have here, and so the value here is the average. So this is the average
not weighted
log
average,
of price
average
for this subgroup. And that's all we do. The prediction is the average of the value of the dependent variable in that leaf node.
Okay, so that means finally, if we have just like 10 leaf nodes, we'll just have 10 values by predicting?
Well, if it was only one tree. All right.
Yeah.
So a couple of things to remember. The first is that by default, we're actually going to train the tree all the way down until the leaf nodes are of size 1, which means for a data set with n rows, we're going to have n leaf nodes. And then we're going to have multiple trees, which we average together, right? So in practice, we're going to have lots of different possible values. Is a question behind you?
So for the continuous variable, how do we decide like which value to split at? Because there can be many values in
We
continuous.
try every possible value of that in the training set.
Everything, which is weird.
Won't it be computationally?
Computationally expensive, and this is where it's very good to remember that your CPU's performance is measured in gigahertz, which is billions of clock cycles per second, and it has multiple cores, and each core has something called SIMD, single instruction multiple data, where it can do up to 8 computations per core at once. And then, if you do it on the GPU, the performance is measured in teraflops, so trillions of floating point operations per second. And so this is where, when it comes to designing algorithms, it's very difficult for us mere humans to realize how stupid algorithms should be, given how fast today's computers are. So yeah, it's quite a few operations, but at trillions per second, you hardly notice it.
Wow.
Masha.
I have a question. So essentially, at each mode, we make a decision, like which category to, which variable to use.
And which split point? Yes.
Yeah, but one thing I can't understand. So we have MSE calculated for each node, right?
Yes.
So this is kind of our one of the decision criteria. But this MSE, it is calculated for which model? Like which model underlies? Like
the model
what do we build?
is for the initial root node is what if we just predicted the average, right? Which here is 10.098. And just the average. And then the next model is what if we predicted the average of those people with coupler system equals false, and for those people with coupler system equals true.
Basically average.
And then the next is what if we predicted the average of coupler systems equals true, year made less than 1986.
Is it always average, or we can use median, or we can even run linear regression?
There's all kinds of things we could do. In practice, the average works really well. There are types of, they're not called random forests, but there are kinds of trees where the leaf nodes are independent linear regressions. They're not terribly widely used, but there are certainly researchers who have worked on them.
Okay, thank you.
And pass it back over there to Ford and then to Jake.
So this tree has a depth of 3.
Yeah.
And then like on one of the next commands, we get rid of the max depth.
Yeah.
Is the tree without the max depth, does that contain the tree with the depth of 3?
Mm-hmm. Yeah.
So is that like by definition? It's
well, except in this case, we've added randomness. But if you turn bootstrapping off, then yeah, the deeper tree will, the less deep tree would be how it would start, and then it just keeps splitting.
Okay.
Okay.
So you have many trees. You're going to have different leaf nodes across trees. Hopefully, that's what we want.
Mm-hmm.
So how do you average leaf nodes across different trees?
So we just take the first row in the validation set, we run it through the first tree, we find its average, 9.28. Then do it through the next tree, find its average in the second tree, 9.95, and so forth. And we're about to do that, so you'll see it. Okay. So let's try it, right? So after you've built a random forest, each tree is stored in this attribute called estimators underscore. 10 means I have my 10 different sets of predictions, and for each one my validation set is of size 12,000. So here are my 12,000 predictions for each of the 10 trees. Right? So
did something happen to the live? Did I lose being live? Am I still live? Maybe. Okay. Hopefully. Okay.
let's take the first row of that and print it out. And so here are what we were just saying. Here are 10 predictions, one from each
hi,
tree.
good morning. Welcome. I forgot to ask you last time, how can I call your name? So please let me know. I can read your even name. But is it Agyadip or... Oh, sorry. Argyadip. There's an R. Why did I see the R?
Okay, and so then if we say take the mean of that, here is the mean of those 10 predictions.
Mm-hmm.
And then what was the actual? The actual was 9.1, our prediction was 9.07. So you see how like none of our individual trees had very good predictions, but the mean of them was actually pretty good. Right? And so when I talk about experimenting, like Jupyter Notebook is great for experimenting, this is the kind of stuff I mean. Dig inside these objects and like look at them, plot them, take your own averages, cross-check to make sure that they work the way you thought they did. Write your own implementation of R squared, make sure it's the same as the scikit-learn version, plot it. Like here's an interesting plot I did. Let's go through each test.
He's expecting too much of his students, and maybe his students are that good, but someone lazy as me says, I mean, I shouldn't be lazy, but someone lazy as me. Anyway.
The 10 trees, right? And then take the mean of all of the predictions up to the ith tree, right? So let's start by predicting just based on the first tree, then the first 2 trees, then the first 3 trees, and let's then plot the R squared. So here's the R squared of just the first tree. Here's the R squared of the first 2 trees, 3 trees, 4 trees, blah, 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 up to 10 trees. And so, not surprisingly, R squared keeps improving, right? Because the more estimators we have, the more bagging that we're doing, the more it's going to generalize, right? And you should find that that number there, a bit under 0.86, should match this number here. Okay? Let's rerun that. Yeah, okay, so that's actually slightly above 0.86. Right? So again, these are all like the cross checks you can do, the things.
Ooh, okay. Let's do this. Or go. Hold up. Let me read this seriously. Or go the. It's a the, it's not D. Or go deep the raft but without the rat. Borat. I guess the last name, okay, but it's O, it's not A. And is it G or is it R? Because I can read the R as well. What happened? I messed up with my my face tracking because I was looking at yeah. Okay. I'm gonna go with or go deep for now. Is it really? Thank you. But tell me if it's the G or the R, which I don't know how you can write that. But for an Arabic system, if you want to say R, say normal G. Got it. In one language, we have only got it. Okay, because like in Arabic, if you write GH, you mean R, you don't mean G. Okay, but I didn't realize it was the, because I've seen that DEEP in other names. Or go deep. Oh, sorry, or go deep. Or go deep. Got it. Hi and welcome. How's I think school isn't back. Is it back yet for you? Because I know you're a student. Yeah. Or go deep. Like, yeah. I think I'm getting used to it now. That's cool. Thank you. I like with my own name, I like it when people take the effort of trying to pronounce it correctly. So that's why I would like to do the same for names that I haven't pronounced before. Let me know how you're doing with learning or school, and in the meantime I will be listening to Jeremy Howard, but please let me know if you have any questions or anything. Oh, okay. Yes, usually today is a holiday though. Ooh, congratulations. What is it? Why is it a holiday? Oh, okay, so you are currently going to uni. Yeah. It's been 2 weeks since, no, I think 1, maybe 2, since like school, all the types of schools have opened, so it's just the beginning. I hope it's not difficult, but I think you are a good student, so I'm not worried.
You can visualize to deepen your understanding. Okay, so as we add more trees, our R squared improves. It seems to flatten out after a while. So we might guess that if we increase the number of estimators to...
Just no scheduled classes. Final year is usually lighter in syllabus. Ah, that's nice. I didn't realize bachelors, like, they get breathing space for their thesis. Or maybe you guys have the style of choosing your own classes and then you planned it out well, because I didn't have the choice to choose my own classes. It was all written down for me for the bachelor's. But like for my master's, I can say the last year was just all free, no classes.
to 20, right? It's maybe not going to be that much better. So let's see, we've got 0.862 versus 0.860. Yeah, so doubling the number of trees didn't help very much. But double it again, 867, double it again, 869.
Oh, it's getting
so you can see, like,
worse? Yeesh. Many colleges have choice of class, but ours is quite traditional, so no choosing. Same. Yeah, we get it. I mean, it's fine not having the choice. It sort of helps. I think having the choice gives you too much freedom, which allows you to mess up. But, like, I think having the path and then letting people choose would be better. Yes. Even in my master's, I didn't technically have choices, but there was an extra class that I could take, which I did. It was fun. Not for CS, yeah. Yeah, I feel like giving 18-year-olds the choice to learn whatever they want, it's not bad if they know, but I feel like 90% wouldn't. Oh, really? That's why you're robotics focused. Electronics and telecommunication engineering. I think you like robotics, right? That's really cool. So you're not bad with hardware. I am terrible with hardware.
There's some point at which you're going to, not want to add more trees, not because it's never going to get worse, right? Because every tree is, giving you more semi-random models to bag together, right? But it's going to stop improving things much. Okay, and so this is like the first hyperparameter for you to learn to set is number of estimators, and the method for setting it is as many as you have time to fit, and that actually seem to be helping.
Okay, so if I go back to my code, which I haven't touched in, I guess, over a day, did we try doing that? We have the shape here, we have the, I feel like my graph is different than his. We try with, oh wow, even my data is different. We try with 20, this is our score. We try with 40, this is our score. We try with 80, and this is our score. Okay. And then we go to the out of bag. What is the out of bag? Let's see. Look at that. His is so much smoother.
Okay. Now, in practice, we're going to learn to set a few more hyperparameters. Adding more trees slows it down. But with less
it make it
trees, you can
exponential?
still get the same insights. So I build most of my models in practice with like 20 to 30 trees. And it's only like then at the end of the project or maybe at the end of the day's work, I'll then try doing like
100?
1,000 trees. And run it overnight.
Ah.
Is there a question? Yes. Can we pass that to Prince?
So each tree might have different estimators, different combination of estimators.
Each tree is an estimator, so this is a synonym. So in scikit-learn, when they say estimator, they mean tree.
Yeah.
So I mean features.
Features.
Each tree might have
Each
different
tree will
combination.
have different breakpoints on different columns.
But if at the end we want to look at the important features,
We'll get to that.
Ah, okay.
Yeah. So after we finish with kind of setting hyperparameters, the next stage of the course will be learning about what it tells us about the data. If you need to know it now, for your projects, feel free to look ahead. There's a
Lesson 2?
lesson 2 RF interpretation is where we can see it.
Interpreting.
Okay, so
Random
that's our first
forests.
hyperparameter. I want to talk next about out-of-bag score. Sometimes your data set will be kind of small, and you won't want to pull out a validation set because doing so means you now don't have enough data to build a good model. What do? There's a cool trick, which is pretty much unique to random forests, and it's this. What we could do is recognize that in our first tree, some of our rows didn't get used. So what we could do would be to pass those rows through the first tree and treat it as a validation set. And then for the second tree, we could pass through the rows that weren't used for the second tree through it to create a validation set for that. And so effectively, we would have a different validation set for each tree.
Is that okay?
And so
to validate?
now, to calculate our prediction,
yeah,
we would average all of the trees where that row was not used for training.
Ooh, that's
right?
a cool
So
idea.
for tree number 1, we would have the ones I've marked in blue here, and then maybe for tree number 2, it turned out it was like this one, this one, this one, and this one, and so forth, right? So as long as you've got enough trees, every row is going to appear in the out-of-bag sample for one of them, at least. So you'll be averaging, hopefully a few trees. So if you've got 100 trees, it's very likely that all of the rows are going to appear many times in these out-of-bag samples. So what you can do is you can create an out-of-bag prediction by averaging all of the trees you didn't use to train each individual row, and then you can calculate your root mean squared error, R squared, etc. on that. If you pass OOB score equals true to scikit-learn, it will do that for you.
That's nice.
And it will create an attribute called OOB score underscore. And so my little print score function here, if that attribute exists, it adds it to the print. So if you take a look here, OOB score equals true, we've now got one extra number, and it's R squared, that is the R squared for the OOB sample. Its R squared is very similar to the R squared in the validation set, which is what we hoped for. Can we pass it?
Cool.
Is it the case that the prediction for the OOB score must be mathematically lower than the one for our entire forest?
Certainly it's not true that the prediction is lower. It's possible that the accuracy is lower.
The R squared.
Yeah. It's not mathematically necessary that it's true, but it's going to be true on average because your average for each row appears in less trees in the OOB samples than it does in the full set of trees. So as you see here, it's a little less good. So in general, it's a great insight, Chris. In general, the OOB R squared will slightly underestimate how generalizable the model is. the more trees you add, the less serious that underestimation is. And for me, in practice, I find it's totally good enough, in practice. Okay, so this OOB score is super handy, and one of the things it's super handy for is you're going to see there's quite a few hyperparameters that we're going to set, and we would like to find some automated way to set them. And one way to do that is to do what's called a grid search. A grid search is where there's a scikit-learn function called grid search, and you pass in the list of all of the parameters, all of the hyperparameters that you want to tune. You pass in for each one a list of all of the values of that hyperparameter you want to try, and it runs your model on every possible combination of all of those hyperparameters and tells you which one is the best. And OOB score is a great choice for getting it to tell you which one is best in terms of OOB score. That's an example of something you can do with OOB which works well.
But what are the hyperparameters? They're not just features, are they?
If you think about it, I kind of did something pretty dumb earlier.
Oh.
Which is, I took a subset of 30,000 rows of the data and I built all my models of that, which means every tree in my random forest is a different subset of that subset of 30,000. Why do that? Why not pick a different, a totally different subset of 30,000 each time? So in other words, let's leave the entire 300,000 records as is, right? And if I want to make things faster, right, pick a different subset of 30,000 each time. So rather than bootstrapping the entire set of rows, let's just randomly sample a subset of data.
Oh, thank you for the answer.
And so we can do that.
Model parameters are like settings for the model defined by user at the beginning. Okay. Then why was he saying going over? So you can set multiple different settings? Because he was saying going over them and using the OOB score. That one made me not think that my understanding was not right, which I didn't have an understanding in the beginning. Even maybe because I think step size is for regression, linear regression, I think, but we're using the random forest, which means even number of trees / estimators could be a hyperparameter. Okay. So, when you are using different hyperparameters, maybe using the OOB score is useful, right? Increasing learning rate, reduce training time, but also reduce optimization accuracy. Oh. Yeah. I'm trying to remember what learning rate was. Okay, yeah. So it depends on the model. Yeah. The different types of hyperparameters. Thank you. Okay. So dealing with the data is also using the OOB score helps us evaluate the goodness of the hyperparameter score set. Yeah, I see. Yeah. Because with the OOB and having different hyperparameters, it's basically you're using different models, almost. And also him saying let's use different 30,000 sets of the data each time, and having the validation set be the part where it doesn't see wow, so many so much variation within just a set of data. That's really cool.
So let's go back and recall proctf without the subset parameter to get all of our data again. And so to remind you, that is, okay, 400,000
This is all of
in
our
the whole
data.
data frame, of which we have 389,000 in our training set. And instead, we're going to go set RF samples 20,000. Remember, that was the site of the 30,000. We used 20,000 of them in our training set. If I do this, then now when I run a random forest, it's not going to bootstrap an entire set of 391,000 rows. It's going to just grab a subset of 20,000 rows. Right? And so now if I run this, it will still run just as quickly as if I had like originally done a random sample of 20,000, but now every tree can have access to the whole data set, right? So if I do enough estimators, enough trees, eventually it's going to see everything.
Is that a good thing?
So in this case, with 10 trees, which is the default, I get an R squared of 0.86, which is actually about the same as my R squared with the 20,000 subset. And that's because I haven't used many estimators yet, right? But if I increase the number of estimators, it's going to make more of a difference, right? So if I increase the number of estimators to 40, right, it's going to take a little bit longer to run, but it's going to be able to see a larger subset of the data set. And so as you can see, the R squared's gone up from 0.86
That's a
to
proper
0.876.
improvement.
Okay, so this is actually a great approach. And for those of you who are doing the groceries competition, that's got something like 120 million rows, right? There's no way
Mustafa,
you would want to create a
welcome.
random forest.
Oh, no. No worries. Don't apologize. Electricity outage this morning. It wasn't fixed until now. No problem. That's super normal. Electricity outage is just a part of our daily lives. I hope you guys are safe, and I hope it wasn't too much of a disturbance, because I think it's almost normal. I hope. Not that I hope, actually. I hope it's not, but anyway.
Forest using 128 million rows in every tree. Like, it's going to take forever.
Oh.
So what you could do is use this set RF samples to do, like, I don't know, 100,000 or a million, or play around with it. So the trick here is that with a random forest using this technique, no data set is too big. I don't care if it's got 100 billion rows, right? You can create a bunch of trees, each one with a different random subset. Can somebody pass the... actually, I can pass it.
The more trees, the more trees you have for the subsets, no matter how big is the data, it would still take time, but like it wouldn't have the same thing as too much data, one model. That's cool.
So my question was, for the OOB scores and these ones, does it take the only like for the ones from the sample, or does it take from all the...
That's a great question. So unfortunately, scikit-learn does not support this functionality out of the box, so I had to write this. And it's kind of a horrible hack, right? Because we'd much rather be passing in like a sample size parameter rather than doing this kind of setting up here.
Okay.
So what I actually do is, if you look at the source code, is I'm actually, this is the internal function. I looked at their source code that they call, and I've replaced it with a Lambda function that has the behavior we want. Unfortunately, the current version is not changing how OOB is calculated. So currently OOB scores and set RF samples are not compatible with each other, so you need to turn OOB equals false if you use this approach, which I hope to fix, but at this stage it's not fixed. So if you want to turn it off, you just call reset RF samples, okay, and that returns it back to what it was. Okay, so in practice, when I'm like doing interactive machine learning using random forests in order to like explore my model, explore hyperparameters, the stuff we're going to learn in the future lesson where we actually analyze like feature importance and partial dependence and so forth. I generally use subsets and reasonably small forests because all the insights that I'm going to get are exactly the same as the big ones, but I can run it in like,
That's really
3 or
cool,
4
isn't
seconds
it?
rather than hours.
Yeah.
Right?
So it does
this
take
is one
less
of
time.
the biggest tips I can give you, and very, very few people in industry or academia actually do this. Most people run all of their models on all of the data all of the time using their best possible parameters, which is just pointless, right? If you're trying to find out like which features are important and how are they related to each other and so forth, having that 4th decimal place of accuracy isn't going to change any of your insights at all. Okay, so I would say like do most of your models on
That was a burn.
large enough sample size that your accuracy is, reasonable. When I say reasonable, it's like within a reasonable distance of the best accuracy you can get, and it's taking a small number of seconds to train so that you can interactively do your analysis. So there's a couple more parameters I wanted to talk about. So I'm going to call reset RF samples to get back to our full data set, because in this case, at least on this computer, it's actually running in less than 10 seconds.
Nice.
So here's our baseline. We're going to do a baseline with 40 estimators.
With OOB score.
And so each of those 40 estimators is going to train all the way down until the leaf nodes just have one sample in them. So that's going to take a few seconds to run. Here we go. So that gets us a 0.898 R squared on the validation set, or 0.908 on the OOB. Now in this case, the OOB is better. Why is it better? Well, that's because remember our validation set is not a random sample. Our validation set is a different time period. Okay, so it's actually much harder to predict a different time period than this one, which is just predicting random. Okay, so that's why this is not the way around we expected. So the first parameter we can try fiddling with is min samples leaf. And so min samples leaf says stop training the tree further when your leaf node has
reached 3 leaves?
3 or less samples in. So rather than going all the way down until there's 1, we're going to go down until there's 3.
Samples? Do we mean like the data?
So in practice, this means there's going to be like 1 or 2 less levels of decision being made.
Or the leaves? 3 leaves each time?
Which means we've got like half the number of actual decision criteria we have to do, so it's going to train more quickly. It means that when we look at an individual tree, rather than just taking 1 point, we're taking the average of at least 3 points.
Oh. Okay.
Right, so we'd expect the trees to generalize, each one to generalize a little bit better. Okay, but each tree is probably going to be slightly less powerful on its own.
Can you
So
visualize
let's
that?
try training that. So possible values of min samples leaf, I find ones which work well are kind of 1, 3, 5, 10, 25.
Odd numbers.
Like I find that kind of range seems to work well. But like sometimes if you've got a really big data set and you're not using the small samples, you might need a min samples leaf of hundreds or thousands. So you kind of got to think about like how big are your subsamples going through and try things out. Now in this case, going from the default of 1 to 3 has increased our validation set R squared from 898 to 902. So it's a slight improvement. Okay? And then it's going to train a little faster as well. Okay, something else you can try, which is, and so since this worked, I'm going to leave that in. I'm going to add in max features equals 0.5. What does max features do?
So this is where we're messing with the hyperparameters, just testing each hyperparameter. I want to read this part. Another way to reduce overfitting is to grow our trees less deeply. Okay. This by specifying min sample leaf that we require some minimum number of rows in every leaf node. I'm gonna need to understand this part better.
Well, the idea is that the less correlated your trees are with each other, the better. Now imagine you had
Different
one
trees, right?
column that was so much better than all of the other columns at being predictive that every single tree you built, regardless of like which subset of rows, always started with that column.
That's cool.
So the trees are all going to be pretty similar, right? But you can imagine there might be some interaction of variables where that interaction is more important than that individual column.
Data versus column, right?
So if every tree always splits on the first thing, the same thing the first time, you're not going to get much variation in those trees. So what we do is, in addition to just taking a subset of rows, we then, at every single split point, take a different subset of columns.
Right. I think he just
So it's
discussed
slightly
that last
different
time.
to the row sampling. For the row sampling, each new tree is based.
Oh, so I see the max features that, right? So the minimum row and then the feature row. So it's data. We're talking about data.
Based on a random set of rows. For column sampling, every individual binary split we choose from a different subset of columns. So in other words, rather than looking at every possible level of every possible column, we look at every possible level of a random subset of columns. Okay? And each time, each decision point, each binary split, we use a different random subset. How many?
Like, it's a really good idea, but also I get confused with the evaluation. Just too many random things. Can you recreate that? I don't know if it's a question that we can ask now, but I am curious.
Well, you get to pick. 0.5 means randomly choose half of them. The default is to use all of them. There's also a couple of special values you can use here. As you can see in max features, you can also pass in square root to get square root of features, or log 2 to get log 2 of features. So in practice, good values I've found are range from 1, 0.5, log 2, or square root. That's going to give you a nice bit of variation. Right? Can somebody pass it to Danielle?
And so just to clarify, does that just like break it up smaller each time it goes through the tree, or is it just taking half of what's left over or like hasn't been touched each time?
There's no such thing as what's left over.
Okay.
Like, after you've split on year made less than or greater than 1984, year made's still there, right? So later on, you might then split on year made less than or greater than 1989. So it's just each time, rather than checking every variable to see where its best split is, you just check half of them. And so the next time you check a different half. The next time you check a different half.
But I mean, like, in terms is as you get like further to like the leaves, you're gonna have less options, right?
No, you're not. You
But-
never remove the variables.
Okay.
In a single tree, that's the case, but not in our version where we're using multiple trees based on multiple features.
You can use them again and again and again because you've got lots of different split points. So imagine, for example, that the relationship was just entirely linear between year made and price, right? Then in practice, to actually model that, you know, your real relationship is year made versus price, right? But the best we could do would be to kind of first of all split here, right? And then to split here and here, right? And like split and split and split.
But
So
if they were binary, I'm saying, like, for
yeah, even if they're binary,
Or like categorical.
most random forest libraries don't do anything special about
Okay.
that. They just kind of go, okay, we'll try this variable. Oh, it turns out there's only one level left, you know? So yeah, that generally they don't do any kind of clever bookkeeping.
Okay.
Okay, so if we add max features equals 0.5, it goes up from 901 to 906. So that's better still. And so as we've been doing this, you also hopefully have noticed that our root mean squared error of log price has been dropping on our validation set as well. And so it's now down to 0.2286. So how good is that, right? So like our totally untuned random forest got us in about the top 25%. Now remember, our validation set isn't identical to the Kaggle test set, right?
Yes,
and this
yes.
competition, unfortunately, is old enough that you can't even put in a kind of after the time entry to find out how you would have gone. So we can only approximate how we could have gone, but generally speaking, it's going to be a pretty good approximation. So 2286.
Top 50 maybe.
Here is the competition. Here's the public leaderboard. 2286. Here we go.
Wow.
14th or 15th place. Okay.
That's
so,
cool.
roughly speaking, looks like we would be about in the top 20 of this competition with basically totally brainless random forest with some totally brainless minor hyperparameter tuning. Okay.
It's not that brainless.
This is kind of why the random forest is such an important, not just first step, but often only step for machine learning. Because it's kind of hard to screw it up.
Yeah.
Like, even when we didn't tune the hyperparameters, we still got a good result, right? And then a small amount of hyperparameter tuning got us a much better result. And so any kind of model, and I'm particularly thinking of like linear type models, which have a whole bunch of statistical assumptions, and you have to get a whole bunch of things right before they start to work at all, can really throw you off track, right? Because they give you like totally wrong answers about how accurate the predictions can be. Whereas with the random forest, generally speaking, they tend to work on most data sets most of the time with most sets of hyperparameters.
And
so,
with
for example,
explainability.
We did this thing with our categorical variables. In fact, let's take a look at our tree. Single tree. Look at this, right? FI product class desk less than 7.5. What does that mean? So FI product class desk. Here's some examples of that column. Right, so what does it mean to be less than or equal to 7? Well, we'd have to look at .cat.categories to find out. Okay, and so it's 0, 1, 2, 3, 4, 5, 6, 7. So what it's done is it's created a split where all of the backhoe loaders and these 3 types of hydraulic excavator are in one group, and everything else is in the other group.
Okay.
So like that's like weird, like these aren't even in order. We could have made them in order if we had bothered to say the categories have this order, but we hadn't, right? So how come this even works, right? Like, because when we turn it into codes, this is actually what the random forest sees. And so imagine, to think about this, imagine like the only thing that mattered was whether it was a hydraulic excavator 0 to 2 metric tons and nothing else mattered. Imagine that, right? So it has to pick out this single level. Well, it can do that because first of all, it could say, okay, let's pick out everything less than 7 versus greater than 7 to create, this as one group and this as another group, right? And then within this group, it could then pick out everything less than 6 versus greater than 6, which is going to pick out this one item, right? So with 2 split points, we can pull out a single category. So this is why it works, right? Is because the tree is like infinitely flexible. Even with a categorical variable, if there's particular categories which have different levels of price,
and it shouldn't take that long, right? Because it should check everything each time.
It can like gradually zoom in on those groups by using multiple splits. Right? Now, you can help it by telling it the order of your categorical variable, but even if you don't,
It should
it's
figure it
okay.
out.
It's just going to take a few more decisions to get there. Right? And so you can see here, it's actually using this product class desc quite a few times, right? And as you go deeper down the tree, you'll see it used more and more, right? So whereas in a linear model, or almost any kind of other model, certainly any non-tree model, pretty much, encoding a categorical variable like this won't work at all, because there's no linear relationship between totally arbitrary identifiers and anything, right? So these are the kinds of things that make random forests very easy to use and very resilient. And so by using that, we've gotten ourselves a model which is clearly, world class at this point already. It's like, probably well in the top 20 of this Kaggle competition. And then in our next lesson, we're going to learn about how to analyze that model to learn more about the data to make it even better.
Okay.
Yeah? Great. So this week, try and really experiment, right? Have a look inside, try and draw the trees, try and plot the different errors, try maybe using different data sets to see how they work. Really experiment to try and get a sense, and maybe try to replicate things like write your own R squared, write your own versions of some of these functions. See how much you can really learn about your data set and about the random forest. Great. See you on Thursday.
Thank you. I mean, is today Wednesday? Wow, how did he know he'll see me on Thursday? That was really smart. Okay. So we were looking at we have the OOB score, the RF sample, which is being reset. Oh wait, no. Hold up. What is that? Decrease max depth. But we have the part where we are doing min sample tree max depth. Okay, so we have the min sample leaf here, which honestly I need to Google it. I mean, I know I can do this, but does that mean I will get an answer? Oh, I didn't run the code. Okay, does that mean I get the answer for that? Yes. Not really. I just want to understand it. Min sample leaf. The minimum number of samples required to be at a leaf node. And we do mean rows of data, don't we? A split point at any depth will be only considered if it leaves at least that many training samples in each of the left and right branches. God, I have a hard time understanding this point. Okay. Each time I'm like, I'll understand better if I move on, and then I move on and other things come up and then I don't understand. But it's okay. We'll understand better if we move on. Okay. So technically I'm 2 lessons in, which is really, really cool. There are 12, but 24 hours of lessons. Yes. It's cool that I was able to do 2 lessons within 1 week. That I'm proud of. But maybe it's not going to be the same when we move continuously. So I'm going to stop here because I don't want to start a new lesson just like that. Yes. Okay. let's close this out. Let me think. Okay, so we can start lesson 3 tomorrow as scheduled. I mean, you see that I don't see what he set out as homework, so I may not try different test data or try just like going over the information. I'm depending on him a bit too much, which is probably not the type of learning he would want from his students, but I'm going through it my way. Yeah, and just the fact that I am able to run the code that he's showing us is cool, and like it helps. Maybe it's not helping it fully. Oh, hi. In Algo, you are splitting the dataset in parts as per criteria, and the hyperparameters make it so that they cannot split in one division. Okay. That has less than 1,000 data points under that category. Let me read that again. Splitting the dataset in parts. Yes, just like how we were splitting per a category, so that you cannot split. If one division has less than, so you're saying, I think you're helped me understand this. If the division you make leaves less than the min sample leaf, so if it's just one row, don't split. If it has at least 3, then split. Is that the case? So like for the category, if we have 3 trucks, 5 bulldozers, even though it's not about that, okay, that was so cool, then it allows it to split, not just one. That was really, really helpful. I don't know why the documentation isn't for, it's not using normal language. Okay, thank you. That was super helpful. Now I have 2 helpers, Mustafa and Orgo Deep, right? So yeah, thanks for being my very helpful helpers. I think I've said it before, I really don't expect you guys to come because like you guys have your own lives, and I'm doing this because I like it. So feel free to not show up because it's your choice. Yeah, today was cool. I got confused quite a bit, but thank you for the explanations. I will inshallah be back tomorrow to start lesson 3 and see how that goes. Thank you. And yeah, I think I don't have anything else, so I should, yes, good for revision. And also I kind of skipped random lessons when I studied ML. Okay, so I hope that is useful. I'm glad that all of us are getting some information out of this. Yes, thank you. I wish you a lovely rest of your day, and the weekend is a bit closer, so I'm a bit happy about that. I will end the stream. Have a lovely rest of your day, and yes, goodbye in 5, 4, 3, 2, and 1. Lift off. Goodbye.